So here we're going to look at a process called the enthalpy change of solution. So we've been measuring lattice enthalpies. Lattice enthalpies tell us about the strength of ionic bonds, and we've found that they're very strong. So why is it that ionic solids dissolve? To understand that, we need to think about all the processes involved. So what is happening when an ionic solid dissolves? So let's just have a look. The first thing we need to do when we've got to dissolve an ionic solid is we've got to break apart the ionic lattice. So we had this very strong lattice. So remember, we had a lattice of oppositely charged ions with strong electrostatic forces of attraction between them. So we're going plus, minus, plus, minus, plus in an endlessly repeating lattice. Now, in order to dissolve that, we need to break apart those really strong electrostatic forces of attraction. So we've got to break the ionic bonds and allow the ions to separate from one another. Okay, so this process here, this is breaking, this is lattice dissociation. We're going from the solid ionic lattice into the gaseous ions. Okay, so they were all packed arranged. Now that's a very large number, and it's represented by the enthalpy of lattice dissociation. But then why would they dissolve? Well, there must be some give back. And what happens is we're going to limit it down to one of each, positive and negative ions, is when you add the water to the ionic lattice, then the positive ion is going to attract the negative parts of water. Now we know that oxygen is more electronegative than hydrogen, so there's going to be some sort of attraction between the positive ion from the ionic lattice and the oxygen's dipole in water. And then attraction is when you form an attraction, it's an exothermic change, and so we're going to give out some energy. Now if we repeat that, the negative ion is going to be attracted to the positive ends of water, so you can imagine like the waters are going to line themselves up around with the hydrogens pointing towards that negative ion. And so we're getting these new attractions between the water and the ions, and that's called hydration. Now hydration is a negative change because it's a forming of an attraction rather than a breaking of one, and so we're going to see energy being given out. Now if the energy we need to put in to break the lattice is smaller than the energy we get back in hydration, then we're going to get an exothermic change. So if you imagine we're putting in some amount of energy to break our solid lattice up, putting in some energy to make gaseous ions, and then we're getting some back. Now if what we get back is more than what we put in, then we're going to end up with an exothermic change, and therefore our solid will dissolve. If what we put in is bigger than what we get back, then we're going to end up with an endothermic change, and we're going to have to put some energy in, probably in the form of heat, to get that solid to dissolve. So we'll just get rid of that little diagram. And we'll carry on here. So the enthalpy that results is called the enthalpy of solution. We'll just highlight that. If there's enough energy left over, it's given out to the surroundings. We'd say that reaction was exothermic. And if there isn't, we need to put energy in, and we say that reaction is endothermic. So exothermic out, endothermic in. So when we get an exothermic enthalpy of solution, we're saying more energy is released on hydration than is needed for lattice dissociation. And if it's endothermic, then less energy is released on hydration than is needed for lattice dissociation. So how do we go about calculating this enthalpy of solution? First thing we need to know is all our definitions. So our enthalpy change of solution is the enthalpy change when 1 mole of ionic solid dissolves in enough solvent to form that solution. So if we think about sodium chloride solid, it's going to form sodium aqueous ions and chloride ions, aqueous. That's the process that we're trying to measure. That is the enthalpy change of solution. Whereas hydration, I'll just correct that, there's a bit of a correction error there, is the enthalpy change when 1 mole of gaseous ions becomes 1 mole of aqueous ions. And so if we were to do that for our sodium gas ions, they could become sodium AQ. Or for our chloride ions to become aqueous chloride ions. State symbols are so important here. Right, so enthalpy of solution could be positive or negative depending on this balance, but enthalpy of hydration is always exothermic, because energy is always released when the gaseous ions form bonds to water. These are called ion dipole attractions, and there's always going to be energy released. So how do we calculate it? We need to go back to Hess's law and remember what we do with Hess's law. So we're trying here to calculate the enthalpy of solution of sodium chloride. So step 1, we're going to write the equation that we're trying to measure across the top. So the enthalpy of solution of sodium chloride is when sodium chloride solid becomes the aqueous solution, where the ions would be separate, because ions separate in aqueous solution. This is our unknown, this is our enthalpy of solution. I'm going to call this X. So this is our enthalpy of solution. So we need to think what we have to do, and we look at what data we've been given. So let's look at the table. So step 2, complete the cycle by looking at what you've been given and putting it into cycle. So let's find some common features. We've got an Na solid here and an Na solid here, NaCl solid, sorry. And so we can see that that NaCl solid goes to Na plus gas and Cl minus gas. So we're going to do Na plus gas and Cl minus gas, and we can see that that arrow is plus 7, 7, 1. Make sure you've got state symbols, make sure you label your arrows. Then what we've got over here is an Na plus gas going to an Na plus AQ. We can see that's happening here. So I'm going to label an arrow pointing up. But also I can see at the same time that Cl minus a gas is becoming Cl minus AQ. So on this arrow, I'm going to add up minus 406 and minus 363. So I'm going to sum that together, that becomes minus 769. But that is the sum of the hydration enthalpies. This side, we were doing turning a solid into its gaseous ions. This was lattice dissociation. So remember what we said? To make a solid dissolve, we need to break the lattice, then hydrate the ions. So then we're going to apply Hess's law, which says it doesn't matter how we get from A to B. So we could go the short way, following X, the thing we're trying to find, or we could go the long way around. We're going to say that X, I'm going to follow the first arrow, plus 7, 7, 1, and I'm going to follow the second arrow, plus minus 7, 6, 9. Our value for X, if we add that on our calculator, it's 2 kilojoules per mole. So the enthalpy of solution of sodium chloride is ever so slightly endothermic. It needs a tiny bit of warming to get salt to dissolve. Let's have a go at another one. So we've got the enthalpy of solution of calcium chloride is what we're trying to find out. Okay, we've been given some data, but let's just make sure we understand what the data is for. So the first one is LF, lattice formation. So the enthalpy change when 1 mole of the solid ionic lattice is formed from the gaseous ions. Now calcium chloride, calcium ions and chloride ions. that arrow is minus 2258. Then we've got hydration of calcium 2+. And hydration is going from gaseous ions to aqueous ions, minus 1577. And then we've got hydration of chloride ions, so from the gas ion to the aqueous ion, minus 363. The other thing we're going to pay attention to in here is calcium chloride. There's a 2 in that formula. We've got 2 Cl- ions. So we need to bear that in mind because our numbers are for 1 per mole for 1. So let's do our enthalpy cycle. We're going to write the equation across the top. So calcium chloride solid is, we're trying to turn it into a solution, which would be aqueous ions. But there would be 2 chloride ions. That's our unknown. That's our X, our enthalpy of solution. Our first bit of information is we've got an arrow that points in, if we look at this equation here, we've got an arrow pointing to calcium chloride from calcium 2+ gas and 2 Cl- gas. And that arrow points towards it, minus 2258, pointing up towards it though. It's a bit different to our last example. Now our next arrow points from calcium 2+ gas to calcium 2+ AQ, and we've got one from chloride gas to chloride AQ. So they're pointing from the gases to the aqueous ions. So we're going up here. And we've got minus 1577, but we've got 2 of the chloride. So don't forget that 2. So remember that formula for calcium chloride has got 2 in it. There's 2 of these, so we've got 2 of this here. Yeah, so we've got this factor of 2 to not forget about. Now if you type that into your calculator, on this side you get minus 2303, and this is our sum of hydrations. And on the left, what we've got is lattice formation because we're forming calcium chloride from its ions. So this time, if we use Hess's law, we can go the short way or the long way around. We can say that X. Now, when we follow the arrow down the left-hand side here, we're going against the lattice formation, so minus the lattice formation. So minus 2258 plus minus 2303. And we type that in our calculator, we get minus 45 kilojoules per mole. Okay, so we're at the bottom, we can see that what we've been doing is lattice dissociation in our first example plus the sum of the hydrations, or if we'd been given lattice formation, it was minus the lattice formation plus the sum of the hydrations.